Hello Year 11 and welcome to the first video here for our third topic. We're looking at linear functions. Now what we're really talking about here are graphs of straight lines. In really simple terms, graphs of straight lines. So linear means a straight line, and a function is sort of like a machine or an operation or a process, right? I put something in, I perform a consistent change to it, and I get something out. What we put in, our input, or if you like our independent variable, is usually x, and what we get out, our dependent variable, because it depends what we put in, is called y, right? That's a function. Now there's a little example here of this function y equals 3x minus 2. That says for your input, multiply it by 3 and then subtract 2 from it. Yeah. Let's see how that goes. Rightio, we'll talk about these other things once we've started. Here's a table of values, and I want to use that function, 3x minus 2. Y equals 3x minus 2. So we could work from left to right. Let's choose something nice here. I'm going to say, well, what if my input is 2? It says to multiply it by 3. 3 lots of 2 equals 6. And then take 2 away. Leaves me with 4. Okay? So this function means that when I put 2 in, I get 4 out. What happens when I put 3 in? Well, I get 3 lots of 3 is 9. Take 2 away, I get 7 out. Right here, you can see how this function is working. Triple your input, take 2 away. Now, triple negative 1 is negative 3, minus 2 is negative 5. 3 lots of 0 is 0, minus 2 is negative 2. And 3 lots of 1 is 3, minus 2 is 1. So there we go, we've filled out a table of values there for this function. This is a particularly nice table of values because my x's are increasing by 1 each time. Now there are two really important properties of a linear function that we'll always try to find, and that's the gradient and the y-intercept. The gradient tells me how steep the slope of the line is when I graph it. And that's the same as telling me, or the way we measure it, is how much y changes when x changes. So when x is changing by 1, how much is y changing by? Right, when I go up by 1, this goes up by 3. Up by 1, up by 3. Up by 1, up by 3, up by 1, up by 3. You can see that because the x's are increasing by 1 each time, the y's are increasing by 3 each time. Right? Every time x increases by 1, y increases by 3. That's my gradient. That's a really important property of a linear function. The slope or the steepness, in fact the rise over the run if you like. Right? We're calculating it this way, saying take, right, for some particular interval on this line, find how much the y increases and divide it by how much the x increases. Really what that's going to give me, when I sort of simplify it, is how much it increases when the change in x is equal to 1. The other thing that we might need to find is the y-intercept, and that is where the graph crosses the y-axis or the vertical axis. Rightio. Now just some things to remember. X and y, I used this term dependent and independent before. Y depends on x. X is independent. That's my input is independent. Right? My output is dependent. Right? My input is independent, and that's my x value usually. And x looks like a cross, and it goes across. Right? The top line of my table, or sometimes it's my first column of my data, usually goes on the horizontal axis, right across the page. Now we need to graph this function here. I've got 5 coordinate pairs now, right? 5 coordinates, right? These pairs of numbers that go together, -1 and -5, 0 and -2, and so on. Now I need to graph this. Looking at my values here, I can see my horizontal axis needs to go from -1 to 3. That's a difference of 4. Now if I just went across 4 squares, it'd be pretty squishy. My vertical axis needs to go from -5 to 7, which is 12. So if that's just one square at a time, well, I think that's going to fit fairly neatly here. I'm going to draw my x and y axis, in this case, at a different scale to each other. Right, it's going to be a consistent scale along the axis, but my two axes are going to have a different scale to each other. Right, I'm going to draw it like this. This is my x-axis and this is my y-axis. Remember, x is across, goes across. And I'm going to use 4 little squares for each x value. That's -1 there. 1, 2, 3, 4. 1, 2, 3. Okay, so they're nicely evenly spaced. Right, we've used up the space that we've got available to us nicely. Right, it is a point when you're drawing graphs that you need them to be an appropriate size, because you might need to read off them, right? And if it's too small, you can't read the detail. If it's too big, it doesn't fit on your page, right? So you've got to get that about right. Now, I want these to go from -5 up to 7 on the y-axis. I'm going to call this -1, -2, -3, -4, -5, -6. Right, that goes down far enough. It's going to be 1 and 2 here, 3 and 4 here, 5 and 6 here, 7 and 8 here. Right, and you can see everything's going to fit fairly neatly in this little bit of graph paper that I've provided. Now to plot these points, remember, we do the top line first. It's the x value, it goes across, so go across -1, across -1 from the origin, across -1 and down to -5. There's my first point. Next one, go across 0 and down to -2. There's my second point. Across 1, up 1. A third one, I can already see they're forming a straight line here. That looks pretty promising. Across 2, up 4 is to here. Across 3, up 7 is here. And it's a really helpful check to see, are they all in a straight line? If one of them should happen to be off, well, check that you've plotted it correctly, check that you've calculated it correctly. Remember, we're dealing with linear functions. You can expect them to form straight lines. Now, use a ruler and a pencil here to do this. I don't have one, but that's worked out okay. And that's y equals 3x minus 2. Yeah. It does ask us to calculate the gradient and the y-intercept. The y-intercept is easy, right? It's where I cross over here. My y-intercept, oops, I should have put a little dash in there. My y-intercept is equal to -2. My gradient, well, what I need to do for the gradient is to calculate the rise over run. I'm going to draw a little triangle in here. This doesn't matter actually where you draw this. It's good if you connect 2 points that you've plotted together, right? That just means that it's pretty reliable. You're less likely to make a mistake, but it doesn't really matter. Right? I'm going to draw this little right angle triangle in here, and my run, right? Well, I've gone from a y value of 1, I've gone up to 7, right? Here's 1 up to 7. My run, oh, that's not my run, that's my rise. My rise has gone from 1 to 7. Right, 7 minus 1 equals 6. My rise is 6. When I have risen 6, how far have I run? It's gone from here to here. I've gone from 1 to 3. Oops, run. Something's on my mind there. The run goes from 1 to 3, or if I want to calculate the length of that, it's 3 minus 1 equals 2. So my gradient is the rise over run is 6 over 2. Therefore my gradient equals 3. That's 6 over 2. Right, so my y-intercept is where I cross the vertical axis. It should have been right there at -2. And my gradient is the rise over run. Okay, very nice. We do have another example here. We'll move through it fairly quickly. Gradient intercept form. Now, if I take a linear function, I can write it in this form: y equals mx plus c. M is the gradient and c is the y-intercept. So back up here, this function, y equals 3x minus 2. Look at this, 3x minus 2. My gradient is 3, my y-intercept is negative 2, right? The number in front of the x is my gradient, the constant at the end is my y-intercept. How convenient. Notice that these are increasing by 3's, and underneath the 0 I've got a negative 2, right? It's all coming together. So if we rearrange a formula, an equation to look like this, y equals mx plus c, then I can read the gradient and the y-intercept off without having to draw the graph and triangles and calculations and things. So here is a linear function. You'll have to take my word for it. Here is a linear function. What is m and c equal to? Well, I said it's the coefficient of x and the constant at the end, but they're both over 3 here, so I'm going to rewrite it. I'm going to say y equals, I'm going to say 6x over 3 plus 1 over 3. Okay, we're just sort of like adding fractions in reverse, right? Same denominator. I know that if I added those fractions together, I've got a common denominator, so it'd be 6x plus 1 over 3. Yeah, that's fine, so I can split them up like that. Cool? Now I'm getting close. I'm going to simplify this 6 over 3, and I get 2x plus 1/3, which means that my gradient is the number in front of the x, the coefficient of x is 2, and my y-intercept is the constant, right? The number at the end is equal to 1/3. Very nice. Finally, just one little point here, positive and negative gradients. Positive gradients go up from left to right, negative gradients go down. This has a positive gradient, this one here. If it went down like this, it would be a negative gradient. Righto, a fair bit to take in there. You will have seen a lot of this before, I imagine. So linear functions have an input and an output. The input is your independent variable, typically x. Your output is your dependent variable, typically y. Linear functions form a straight line when I graph them. The gradient, or the slope, or the steepness, or the rise divided by the run is your gradient, and that's the number in front of in front of x when I write it like this. And where it crosses the vertical axis is my y-intercept, and that's the constant on the end. Positive gradient goes up, negative gradient goes down. I think that's it. Hope you enjoy. See you in class.